Hello and welcome to Lesson 8.1, Equations of a Line. So today we're going to take a look at some equations of lines using actually vectors and various different forms of those equations. So a line can be described using either a vector equation or a parametric equations. So let's say we have the line over to the right that we have here, that we see in the color red, and it continues in both directions. What we're going to do is we're going to let r equal any point on this function x on this line being related to the vector xy. So let me draw an example. This is one possible point. That could be a result of x and y. So it's created by creating what's called a position vector. What we do is we start with that position vector, x0, y0, that's where we start, and then we increase by any multiple of a vector AB, which is its direction. So from going in that same direction, this is our vector AB. That'll give us any other point on the function like this. But we have to make some kind of multiple of AB. So what we can do is we can create what's called our vector equation. Which we describe as either the vector r as the starting at x0, y0, and adding any multiple of AB, or you could have instead used x comma y as x sub 0, y sub 0 plus any scalar multiple of a times b, where this value t is some real number. Or what you could do is you can create what's called the parametric equations. And the parametric equations specifically look at the x and y components separated. So it looks at x being equal to x sub 0 plus t times a, and it also looks at y equal to y sub 0 plus t times b. This second option, these parametric equations, can sometimes be a lot easier to work with than having to use the vector equations. So let's see how this works out. So the line passes through the points 2, -3, and -1, 5, listed as L and M. What we want to do is we want to determine the vector and parametric equations. With that information, we want to see if the point -4 and -11 exists on the line. And then we want to also determine the intercepts of this line. So we're going to start with part A here. To do that, we're going to find the vector LM. You can pause your video at this moment in time and show that you can work out the vector LM. Okay, so in this case, our vector turns out to be -3 and 8. Now, if you did ML, just realize that you'll get the values of 3 and -8. Not much different, it's just the opposite direction. Values are negative values. So what you can do is you can come up with one possible vector equation. And there can actually be multiple vector equations. I'm going to use a short form for equation right here, EQN. So to come up with your vector equation, you select your starting or reference point, you can use either of these reference points, L or M, or anything else on the line, plus any scalar multiple of your direction. And that's all you need for your vector equation. So in actual fact, you could have multiple vector equations. To come up with your parametric equations, you come up with the same idea here. You just separate the x and y components, and you can actually have multiple answers here. So these are your possible parametric equations and vector equations. And again, you can have multiple answers, and therefore the textbook may have only one of these answers and might not be the same value that you have. So don't worry if it's not the same. Okay, so part B. What we want to do is we want to see if the point -4 and -11 actually lies on this line. So that means our value of -4 is one possible value for x, so I'm going to substitute it into my parametric equation there. And that also means -11 is my y value on this parametric equation as well. Now, in order for this to be true, that scalar multiple t has to be the same. So what I'm going to do is I'm going to solve this equation. So I'm going to rearrange the 3t to this side. And I get t equals 2. So if I move 8t to this side, -8t, -3 plus 11, -8t equals 8. That means t equals -1. So since these t values are not the same, therefore we've shown that -4, -11 is not on this line. These t values would have had to be the same in order to be on this line. So, what we can do, however, is find intercepts on this line if they exist. So that means if I want my x-intercept, I need to find when y equals 0. So I'm going to substitute 0 in for y to my to my parametric equations. And I'm going to solve for t. So this has to be the t value to give me my x-intercept. So I'm going to substitute this into my x value for my parametric equation. And then I'm just going to solve. So this becomes 2 minus 9/8. Well, 2 is the same as 16/8. So 16/8 minus 9/8 is 7/8. So that means my x-intercept is 7/8 and 0. I can do the same process and figure out my y-intercept. So if I want my y-intercept, x has to equal 0 here. So here t equals 2/3. And again, you can pause the video right now and figure out what your y-intercept is. go. That's how you work out your intercepts. Okay, so let's take a look at another problem here. Maybe an application of these kinds of things. So here we have two lines, and because we can find different vector or parametric equations of lines, I want to see what would happen if we want to see if these two lines are the same. So r is either 1, 3 plus s times negative 2, 6, or 5, negative 4 plus t times 1 minus 3. Well, what you might notice is these two directional vectors right here are collinear. In other words, you might remember that negative 2, 6 is equal to negative 2 times 1, negative 3. That's what it means to be collinear. They're scalar multiples of each other, or parallel. So that means at least these two lines are parallel to each other. I just need to determine if it's the same line or different lines. So currently, I know these lines could be parallel, could be the same. Well, in order to verify that they could possibly be the same line, what I need to do is just see if the reference point, or the starting point on one of them, is on the other function, or on the other line. So I'm going to label these two lines. I'm going to call this L1, I'm going to call this L2, so that I can refer to each line. So maybe we can find our parametric equations for one of these lines. Oops. Let's do L2. So write down your parametric equations, pause the video, and work that out. Okay, so now what we need to do is check if 1 and 3 is on line 2. So I want you to pause your video and check. Okay, so let's see. Get a t value of negative 7 over 3 here. I also get a t value of negative 4. So that means these lines are parallel. Okay, so there we go. Let's try another item. Well, this can be kind of disconcerting that we have multiple different equations for the same line. So another way to describe a line, let me draw a line again. Is to describe a line based on its normal. So we looked at this idea. Oops. Let me fix that. We talked about this in our last unit a normal is a vector that is perpendicular to the original vector. So what we're going to do is we're going to call this vector n, and we're going to give it the letters A and B. Well, how does it relate to the direction of this vector, of this line? Well, if we remember, the direction has to have the dot product between A and B, and its direction as 0. So that means this has to be probably B, comma, negative A. Or negative B and positive A. So a Cartesian equation, this is where we're going to get, or a scalar equation, also means the same thing, is given by ax plus by plus c equals 0, where these values of capital A and capital B are actually the normal of this function. With x sub 0 and y sub 0 as a point or a reference on this function, on this line, and the value of c actually works out to be value that's a combination of a times x sub 0 plus b times y sub 0, all the negative of that. Something else that comes out of this, when you actually create this, your values of a, b, and c turn out to be integers. And your a value also turns out to, more commonly, you have to put it in this form, has to be greater than 0. If it's not greater than 0, then you just have to multiply the entire equation by negative 1. This, what it does is it creates one equation all the time for all lines. This equation, you might realize, you saw in grade 9, this is called standard form. So, let's show you how you can work out the scalar equation, or Cartesian equation, of such a line. So find the scalar equation of a line that passes through the point 1, negative 2, and negative 3, 4. So first off, we're going to find our direction. So, pause your video, work out the direction of this line first. Well, you might find out that is, I'm just going to subtract these two from each other. So I get a value of 4 and negative 6. So, what I now need is my normal vector. Remember, it's the same values, just reversed order. Change one of them to a negative. So I would strategically change the 6 into a positive there, or change the sign. You can also write the normal right here as, instead, 3 and 2. You can always reduce directions and or normals to be smaller sizes, and it might help with some of your calculations. So, now what we can do is we can work out this equation with the fact that we have a point on the line. So you can start out with 3x plus 2y plus some unknown value c, which we're going to work out, equal to 0. So what you do is you just take one of your 2 points, either 1, negative 2, or negative 3, 4, and substitute in for x and y. And then you just solve for c. And therefore you get a scalar equation of 3x plus 2y plus 1 equals 0. Now it'll turn out to be the same value, or the same equation, no matter which point you chose, and also if you had started with 6, 4 instead, and then reduced later. Make sure you always reduce your expressions to lowest terms. And there we go. There's our scalar equation. Now, so far we've only been looking at equations of lines in two-dimensional space. Well, in three space, they can also be expressed the same kind of idea. So a vector equation in three space can be listed as r equal to x sub 0, y sub 0, z sub 0, same reference point, plus some scalar multiple of a, b, c. So as you can see, you're just adding an extra dimension. And therefore, its parametric equations now deal with three equations. So, similar properties exist with these. Okay, so line goes for the points 2, 2, 2 and 1, 0, negative 1. We want to determine whether or not we can determine our vector and parametric equations for this line. And we want to see, does the point negative 3, negative 8, negative 13 actually lie on this line? So again, first things, I want to find my direction. You can pause the video now and find your direction. So you should find it as one possible direction is 1, 2, 3. Ooh, it's like I made that on purpose. So one possible vector equation is, I'm going to use a reference point 2, 2, and 2, plus some scalar multiple of 1, 2, 3. And my parametric equations are x equals 2 plus t, y equals 2 plus 2t, and z equals 2 plus 3t. Okay, so part B. Find if the point exists on the line. So again, we've already seen something like this. Give it a try, see if you can figure out if this point lies on the line. Pause the video at this moment. Okay, so I'm going to work it out, showing you. There's one t value. Ooh, this looks good so far. You gotta check out all three though. Gotta make sure it works. Don't assume. Oh, this t value also equals negative 5. So that proves that this, therefore the point, negative 3, negative 8, negative 13, lies on the line. And there you go. Thus concludes this lesson.